Alrighty, so we want to talk about the squeeze theorem. So, just for credit, where credit is due, I'm looking at math.ucdavis.edu. There's a beautiful PDF there that I found, and that is called Limits Using the Squeeze Theorem. And I really like this document because it explains in pretty much one page what the purpose is, when the squeeze theorem is useful, and also gives a lot of good examples. So I'm just giving credit to that because I did not come up with my own examples for this. Anyway, so the squeeze theorem is used when other methods are not working. So for example, you've tried conjugate, you've tried factoring, you've tried even trig identities maybe. You've used your special limits that you've memorized, but nothing is working. So the squeeze theorem is really cool. And the squeeze theorem can be used to solve a lot of horizontal asymptote problems. So I usually use it for HA questions, limits at infinity type questions. I like to use it on problems that involve x goes to 0. But like I said, I've tried everything else. But, honestly, I'm sure you can manipulate most questions first and then use squeeze theorem. As long as you're dealing with some kind of infinity or 0, I've found that's when I use them the most. Okay, so what I'm saying is if you saw a problem, let's say you saw a problem like this. So this will be my first example. Let's say x goes to infinity. And then it says sine x over x squared, right? So we've already done a problem like this. This problem isn't hard to understand. We know there's a function that basically approaches the x-axis. We know this from intuition mainly. So we know that this function basically wiggles and follows towards the x-axis. It has some negative features. It has some positive features. And that's because the top can be any number between -1 and 1. Including -1 and 1. So we know that if the top is always a number between -1 and 1, and if the bottom is always positive, we know that the function will have some negative behavior. If you're dividing negative and positive, for example. We also know that it gets smaller because the bottom can become, 400, 4,000, 4 million. If x was, let's say, 20, or if x was, 40,000, x was 200, x was 2,000. So basically, the bottom is much larger than the top ever will be in terms of absolute value. So we already know then that intuitively we know that y equals 0 is the horizontal asymptote. And the same is true on the left side, actually. The same is true over here, because basically that denominator is going to be the same exact denominator, and the numerator will be similar as well. So we also know this is an odd function, so whatever's happening near the origin is symmetric with respect to the origin. So if it goes towards 0 here, then it comes from underneath here. So there's that odd symmetry there. Actually, this function I don't believe does approach the origin. But let's say this side goes down to negative infinity, this side would go up to positive infinity. Just get that odd behavior. Or if this goes to -1, this would go to +1, kind of a thing. Whatever. We don't care about that, right? We care about the horizontal asymptote. So how do we prove this, though? See, that's the question, not what do we think the horizontal asymptote is or what do we think the limit is. It's really a question of how do we prove it, right? Because we could look at a table of data and get an intuitive guess, right? So the squeeze theorem gives us a chance to do that. And actually, you might be surprised to find that the starting step of these sorts of proofs is this one, actually. So this will actually be step 1 of our proof. Okay, so let's take a look at how we would do this problem. and get the same answer that we got down here. This is the correct answer, naturally. Okay, so about to prove it, we're going to actually start with the fact that -1 and +1 are the boundaries of sin x. So that's step 1. Okay, step 2, we're going to try to manipulate this middle sin x, eventually trying to get it to look like the original question. So in this case, since we already have sin x in our original problem, and we have sin x here in our step 1 work, we would just find ourselves dividing by x squared. Now, where do we divide by x squared? Well, certainly in the middle, right? But also on each side. See? So what I did was I took step 1 and I divided everything by x squared. You might say, well, what if you divide by 0? Okay, yeah, that's a concern. Good news is I'm not going to divide by 0 because I know that the x's I'm interested in for this problem are large positive x's. So it's perfectly okay to just divide by x squared here. There is no need to worry about x approaches 0. You can just say x is large and positive. You could say x is positive. You could say x is not 0. There's a few different ways to sort of give that little disclaimer, right? Little disclaimer. So we're not saying that this statement is always true. We're just saying it's true for positive x's or x's that aren't 0. Actually, it's true for negative x's also. Okay. But notice how easy step 2 really was. I mean, I just divided step 1 by x squared. Okay, step 3, we're going to put that lim statement back in. So L-I-M, you're going to put that there. You're going to put that, for now we'll just write lim. We'll put that there. We'll put that there. So the statement we had was what we call a compound inequality. We have basically 3 statements, right? We have 3 expressions. We have these 3 expressions here, 1, 2, 3, and I just basically put a limit on each one. 1, 2, 3. Remember, this is a limit question, so it's time to sort of bring that into the mix. We have actually ignored so far the whole limit thing, right? In our work here in blue, we have not written LIM until now. Okay, now which limit do I want to put? Like, do I want to put x goes to 5 here? Of course not. I'm trying to prove a limit at infinity, so I'm going to go and put infinity there for all 3. So just like you can multiply, everything here by 6 if you wanted, right? You can multiply everything by 6. In the same way, you can certainly find limit. And I won't prove that. I'll just let you believe me on that. Okay. Then step 4. Okay. So what I usually do on this one is I write an L here. And the reason I write an L there is because I want you to understand that L is our answer. See, L is whatever the answer will be. So just sometimes we say, solve for x or solve for p or whatever. We're going to try to solve for L. And this is a good thing to do because this statement here is quite large and intimidating and even distracting, especially if all we're trying to do is solve for what that middle thing is. And what we're going to do is really a neat trick. We're going to solve this question here, which is easy. And we're going to solve this question here, which is easy, even though this question in the middle is hard. So we have 3 problems to work on. Let's start with the easy one. So the first one, you could pull the negative out if you like. And the last one, and the first one look now pretty much the same. Now, let's see here. I'm going to do some work, I guess. Is there any work to do, really? I mean, we talked about this kind of a thing in earlier videos, like, don't we have every reason to believe that this is just negative 0 and 0? I mean, we don't need squeeze theorem for that. I mean, we don't need any fancy techniques for that. We know that x grows and 1 doesn't. So we basically get 0 is less than L is less than 0. And now let's go do the problem in the middle that's really hard. Oh, wait. We don't need to. If our answer, if L is the answer, and if L is whatever the answer will be, and if it has to be between 0 and 0, then we know that L is 0 before we even bother to examine it any further. So this is a very clever trick, and now you can write your final conclusion, which is the limit x goes to infinity sine x over x squared is 0, and then you could put by the squeeze theorem. So what just happened? Well, we basically solved a problem by not solving it. We solved similar problems. Now, here's what I don't want you doing. I don't want you to say, well, I'm just going to find 2 easy questions to solve, and that will always tell me what's in the middle. No, you have to start with a true statement here. See, you have to start with something that you know is true here. You can't just make up, 2 problems, one on the far left and one on the far right. You have to start with a true statement, like sine x is between -1 and 1. And everybody believes that. Everybody knows that. And everybody knows you could divide by x squared. And everybody knows that you could put a limit all the way in there. And everybody knows that the one on the left and the one on the right are easy. And everybody knows that they're 0. And everybody knows that if something's between 0 and 0, it has to be 0. And so therefore, the squeeze theorem is appropriate in this context because we chose a range statement that we know and trust. Let's try another one. Let's say, for example, 2, I gave you this one instead. Inverse tan x over 3x plus 5. And then let's say we did limit x goes to infinity. Like that. So for this problem, I wouldn't start with sine x is between -1 and 1, right? I wouldn't do that. I would start with tan inverse x is between -pi/2 and pi/2. Now, how do I know this? How can I be sure about that? Well, it's actually a pre-calc statement. This is actually from pre-calc. And I wouldn't really expect all of you to remember it, except to say that you've seen once upon a time, you saw the graph of tan inverse. Tan inverse looks like this. We call it inverse tan. We call it arc tan. And if you remember, there was a horizontal asymptote here and a horizontal asymptote here. And hopefully you knew that. If you didn't know that, just be warned. This graph is quite popular. So if not last year, then definitely this year. Okay? All right. So see what I've done here is I've started with a true range statement. This is a true range statement. I know this is true. Okay. Now I'm going to divide by 3x plus 5. Oops. So I'm going to divide by 3x plus 5 there. I'm going to divide by 3x plus 5 there. And I'm going to divide by 3x plus 5 there. Okay. Now I'm going to put the LIM statement back in, specifically limit at infinity, because that's the kind of question we're doing. 1. Ooh, that middle guy is so ugly. I'll go ahead and write it. I don't want to be lazy. I want to model good behaviors. We have tan inverse x and 3x plus 5. And then we have limit again. This part's kind of annoying, writing all of this. But remember, this is a proof, right? So if you're doing like all these shortcuts or whatever, that to me is not helpful. Guys, this is the stuff that your teacher grades, right? On limit questions anyways. Okay, now for this one I can pull out the pi over 2. That's just one of the properties of limits. You're welcome to do that. You know what? I said before that this middle part, let's just write it as L. It's just easier. Okay. And then over here, you can pull out the pi over 2. Okay. So this is 0, as we know from our studies earlier in the videos. And then this is also over here 0. So we have it here again. 0 is less than L is less than 0. And that means L is 0. Now, this one has a strange ending, doesn't it? If you think about it, it has a very strange ending. L has to be smaller than 0 and bigger than 0 at the same time, right? And if you ignore this middle, 0 has to be less than 0. So there's something fishy about what I wrote here. And in a more formal math class, we would have to address why we would have to address some of these nuances, like why are we allowed to say L is exactly 0 if it's not something, well, this statement here technically has a different meaning than down here. And technically this statement here has some philosophical issues. This statement here has some philosophical issues. Right? How can L be less than 0, greater than 0? And how can 0 even be less than 0? So we probably should have used some absolute values here or something. But I don't want to stress too much about that. This is just introductory squeeze theorem, and I think it's fairly convincing that you guys would trust that it is 0. All right? Okay. The other thing that the squeeze theorem is good for is problems where x approaches 0 instead of infinity. And I also want to remind you of something. Every question that is an x goes to 0, x goes to infinity question, right? If you have an x goes to infinity question, and let's say this is, I don't know, let's say it's a cosine x plus 5, so basically 5 plus cosine x. Let's do 5x plus cosine x all over 2x plus 8. Let's just pretend. Okay, and then maybe all of this is square rooted or something. So this problem can also be written as an x goes to 0 problem. So for example, 3, for example, I could give you, x goes to 0 plus, and then 5 over x plus cosine 1 over x, 2 over x plus 8, and these are the same question. Right, so I'll let you think about why these are the same. Well, they're different questions, but they have the same answer. One of them is just a rewritten version of the other. Okay, so this is why I say squeeze theorem is also good for x goes to 0 problems. So let's say that somebody gave us a question like this, we would just immediately convert it back to what you see at the top. Oh, sorry, I forgot the square root. Yeah, so these are the same answer, basically, whatever these are. And let's go ahead and start this question. So if this is where you started, you would say, okay, hold on. What about all those 1 over x's? Do we need all that? Nah. Let's write this as x goes to infinity, positive infinity, and then we'll write this as square root 5x plus cosine x, just regular cosine x, and then 2x plus 8. So again, these are the same question. You might have to rewatch part of one of my earlier videos. Okay, so now what? So now you can apply the squeeze theorem, right? So we know that cosine x is between -1 and 1. We know that if you add 5x to everything, right? You add 5x to each part of this. So you add 5x to the -1, you add 5x to the cosine, you add 5x to the 1, then you divide everything by 2x plus 8. Same thing here, divide by 2x plus 8. Then you write limit, specifically x goes to infinity. Oh, you know what I forgot? I forgot the step where you square root. Then you square root everything. And lastly, here, proofs are always a pain, right? Writing out a proof is always a lot of work. Then you write limit x goes to infinity, square root, 5x minus 1 over 2x plus 8. Limit x goes to infinity, square root 5x plus cos x. So I'm going kind of fast. And lastly, limit square root 5x plus 1 over 2x plus 8. Okay. And I forgot one little thing here. No, I didn't. Okay, this is correct. Okay, so this will be our L in the middle. Okay, a little bit more work here. I would probably do square root of limit x goes to infinity. Oops. And then it's 5x minus 1 over 2x plus 8. And then over here, limit x goes to infinity, square root. Well, let's do square root outside, right? That was the whole point of this next step here. So that's also one of the properties of limits. You can pull out that radical or any rational power, really. This is a half power problem. All right. Now, this is interesting. See, this is really interesting. So this one comes out to square root of 5 halves. And this one does too. So L is basically square root of 5 halves, or square root of 5 over square root of 2, or square root of 10 over 2. All right, so that was a little hard to believe, right? I mean, that was kind of weird. Let's see if it is actually true. So what I'm going to do is I'm going to go to my Desmos app. So where's my Desmos app here? There it is. Okay. I'm going to type this original question, which was just, fx equals, and let's see if I remember this here. So the top was a 5x, oops. The top was a 5x plus cos x, I believe. And then the bottom was a 2x plus 8. Oh, I forgot that square root. Maybe I can still make it work here. And then we'll put parentheses around that. And we'll just do a half power, if you don't mind. Okay. So the whole question was about, what is the limit at infinity? So as you go to the right, what y coordinate is this approaching? And the answer I got was the square root of 10 over 2. So now let me write y equals square root of 10 over 2. Yeah, for sure. Let's make that green and dotted. Yeah, that is definitely the right horizontal asymptote. So that was a very beautiful problem, and we solved it by squeeze theorem. Now, are there other ways? Well, yes, but never quite as convincing as this, because everything else that you try to do, let's say you're trying other ways to do this problem, you basically run into that question of what happens to cosine, right? Cosine is really the awkward part of this problem. If you look at some of the other techniques we tried, right, in our other videos, you pretty much would have to ignore that cosine. Whereas here, what we did was we actually started with the cosine, and we treated it as a number between -1 and 1 and built our whole case around that. You can also give a strong verbal explanation for this problem. You could say, well, when x gets extremely large, and especially as it gets larger, not large, the cosine x becomes less and less significant because the 5x will continue to grow and the 2x will continue to grow. But these here don't really grow. They just kind of become, spit in the ocean and insignificant. And this would give you square root of 5/2. But see, that's sort of hand-waving arguments, right? I mean, that's a strong argument. It's better than hand-waving, but it's just not as convincing as this. This is very, very convincing. And mathematicians want to get the right answer, but they also want to have convincing proof of things, right? And there's a few things I didn't prove here, right? I never proved the orange statement at the top, and nor did I prove that this right here gives me this right here, right? But those things are assumed because we learned that sort of thing in either pre-calc or earlier in the videos, right? So you don't have to prove everything, but you have to start at a place where this is where we're at. We know statements like -1 is less than cos is less than 1. We know that the limit of 5x minus 1 over 2x plus 8 is 5/2. So you start with what you just learned, yesterday or 5 days ago or a year ago, and you build your case with those kinds of statements. Kind of like when you use the vertical angles theorem in geometry, but only after you learned it, right? Okay. So very beautiful problems and very creative and clever. Let's do one more. This one is directly from the UC Davis examples. I think this is example 4, actually. Yeah, this is actually example 4. So we have limit x goes to 0 minus, and we have x cubed cosine 2 over x. Okay. So remember that whatever's happening at x goes to 0 minus basically means that you're approaching 0 from the left side. And who knows what that graph is going to do, right? It might approach the origin. It might shoot up to infinity, right? So that's the question, obviously. Also, we know that 0 minus means small and negative. Small and negative. Okay, let's use our trick where we insert 1 over x's. So let's say that you took out each of the x's here and you changed them to 1 over x's. What would this question look like then? That's been a handy trick. We even used it in the last example. So this would be a 1 over x cubed, and this would be a cosine 2 over 1 over x. In other words, this question would basically be cosine of 2x over x cubed. What would happen to the limit statement? Well, it wouldn't be O minus, right? Because basically you would also change this x to a 1 over x. So this x changes to 1 over x, this x changes to 1 over x, and all of them do, right? All of them change to 1 over x. So this would be a 1 over x approaches O minus. But 1 over x approaches O minus implies that x is approaching negative infinity. So I'll let you think about that. Pause the video if you have to. Right? If 1 over x is tiny and negative, then x is large negative. So like negative a million, negative a billion, negative a trillion. Okay? So you might want to memorize some of those little statements as well, like little simple facts like that. It helps. Okay, and then this one we could do squeeze theorem. So cosine 2x, just like cos x, is also between -1 and 1. So let's write a little note here that we're using the squeeze theorem. This is just a note to self and to your readers. This is -1 over x cubed cos 2x over x cubed 1 over x cubed. Throw that limit back in there. We could put the negative out front on that one. L notice that every one of these problems is the same kind of limit. That's the limit at negative infinity. That's the limit at negative infinity. The difference, only difference, between the leftmost simple problem and the rightmost simple problem is this negative, which came from the -1 here. Okay. And hopefully you can convince yourself that this is 0. And so is this. So L is 0. So that means a couple of things, right? It means that the original question, right, which was a very strange graph, right? This is a very strange graph, I'm sure. This function does approach 0 from the left side of 0. So in other words, the y approaches 0, just like x is. Let's go look. All right, so the question, the question was, let's erase this problem. It was x cubed, and then a cosine 2 over x, like that. And although this problem is, like I said, very complex, we were really interested in what's happening on the left side of the origin. So let's zoom in there, the left side of the origin. And you'll never get a good enough zoom, right? It's there we go. So just specifically focusing on the left side, or you can go up here and in braces, right? Use braces to write x is less than 0. So that way you can just focus on what you need. This is the graph, and it clearly approaches y equals 0 as the x also approaches 0. Right. So as you go from left to right, you approach y equals 0. Okay, but this also means that if you did g of x, which is equal to f of 1 over x, that this graph approaches negative infinity. So now look at the green graph and go to the far left. There's a horizontal asymptote of y equals 0. By the way, when I say gx equals f of 1 over x, I'm just saying that there's a new graph, basically the same equation you see up here, right? Same equation as this top one, but with all the x's replaced upside down. And that's basically, that's the one that was 1 over x quantity cubed, and then there's a cosine 2 over x. Okay, so that purple graph is the same as the green graph. We'll make them both purple. But you can see it's easier to type g of x equals f of 1 over x. Okay, so basically oh, that's interesting. The purple one's double-sided. That's very interesting. Let's make sure that we're just looking at the left side, because we care about x approaches negative infinity, right? We don't care about x on the right. Okay. And then right here too, we'll put in just the left side. Okay, so just only the left side of 0. So there's 0, if you can barely see it there. And there's some really odd, really awkward behaviors going on. But more importantly, if you're looking at Actually, sorry. Wait, hold on. These purple graphs are not the same. Give me a second. Oh, I know why. This should have been, I'm so sorry, this should have been a 2x. I need to start over on this graphing phase. Sorry, just ever since I opened Desmos, I've shown you the wrong stuff. Okay, the red graph is the original question. And we're looking at what happens as you move from left to right towards the origin. You approach y equals 0, right? Okay. Then the purple one is basically, it doesn't matter which of these you use. These purples are the same graph, right? But basically, that one, we're not going to look at the origin. We're going to look way over here on the left. And you can see that there's a horizontal asymptote at y equals 0. A little bit hard to see. Okay. So I had given you the wrong red graph. That's why it was confusing. And there you have the squeeze theorem. So I really enjoy it. I think it's a really cool trick slash technique slash convincing argument to confirm some things we probably already knew. All right, there you have it.